Hello, my name is Monica Valcavi and I will be presenting on spaCy, as well as describing what it is, why I chose a tool, and presenting two simple examples of what the tool is able to do. I will begin with an overview of what spaCy is. spaCy is a natural language processing tool published under the MIT license. spaCy version 2 has an accuracy of 92.6%. This version was published in 2017. It is considered to be the fastest syntactic parser. More accurate systems than spaCy are slower by roughly 20%. spaCy is equipped to handle deep learning workflows and has the ability to be integrated with other tools. There are a couple reasons as to why someone can choose spaCy. It provides a starting point in NLP for beginners. It also allows for production from end to end, unlike NLTK. It is often used in production, whereas another commonly used tool, NLTK, is more used in research. spaCy provides the ability to support training on a user's own data and allows for the end product to be a CPU efficient product. Oftentimes, it can have faster runtimes than NLTK. Unlike NLTK, it allows for neural network models and integrated word vectors. However, not every tool is perfect, so there are some downsides to spaCy. Sentence tokenization is slower than NLTK. If this is something that would affect the use case, NLTK might be a better option. There are not very many languages supported. There are 7 supported languages, as well as a multi-language model that supports multiple languages, and it doesn't have very flexible use cases. This is probably why it's most often used in production environments and why NLTK is used in research, because it's more flexible and there are many more use cases. I also wanted to provide a brief overview on the architecture of spaCy. spaCy contains container objects, processing pipeline, and other classes. The container objects are doc, span, token, and lexeme. Doc is a container for accessing the annotations. Span is a slice from the doc. Token is an individual token, such as a word, symbol, any white space that might be present within the corpus. Lexeme is an entry in the vocabulary that has no context, so there's no part of speech, no dependency to that object. Processing pipeline contains language, tokenizer, lemmatizer, morphology, tagger, dependency parser, entity recognizer, text categorizer, matcher, phrase matcher, entity ruler, sentencizer, as well as other functions. A language is a processing pipeline. It is loaded as NLP and then used in the application. Tokenizer segments text and creates the doc. Lemmatizer determines the base of the word. Morphology assigns linguistic features to the word as well as its part of speech tag. Tagger annotates the part of speech tag within the objects. Dependency parser annotates the syntactic dependencies on the objects. Entity recognizer assigns entities such as persons or products on the objects. Text categorizer gives a category to the objects in the doc. Matcher matches the sequences of tokens based on the pattern rules. Phrase matcher matches the sequences of tokens based on their phrases. Entity ruler adds the entity spans to the doc using a set of token-based rules or phrase matches. Sentencizer implements custom sentence boundary detection logic that isn't dependent on the dependency parse. Other functions can be applied depending on the size of the application and how in-depth the example must go. The other classes that are present are vocab, string store, vectors, gold parse, and gold corpus. Vocab is a lookup table for the vocabulary that allows you to access the objects in lexeme. String store maps strings to form hash values. Vectors are a container class for the vector data that is keyed by the string. Gold parse is a collection for training annotations, and gold corpus is an annotated corpus created using JSON. It manages the annotations for tagging and dependency parsing. The image provided shows how all the interworking parts intertwine with one another. spaCy has many features. I will be focusing on the linguistic features later in the presentation. Rule-based matching allows for a user to find specific words and phrases and provides them with tokens and relationships. Matching can be token-based, phrase-based, or entity recognition-based. These can also be combined depending on the user's needs. The pipelines allow for a document to be processed in several steps. Pipelines consist of a tagger, a parser, and an entity recognizer. These pipelines can also be customized for a user's needs. Similarity of words is calculated through the use of word vectors. They are commonly generated using word2vec. These vectors can also be customized. It also supports models for training. There are 3 forms of visualizers that are used in spaCy. They could be dependency parsed, entity recognized, or long text. The dependency parser recognizes the word dependency within a sentence. Entity recognizer recognizes each entity within the sentence and identifies them. For longer corpora, it is possible to visualize individual sentences. This requires them to be passed individually through the visualizer. There are 7 major aspects of the linguistic feature of spaCy. They are part of speech tagging, dependency parsing, named entity recognition, entity linking, tokenization, merging and splitting, and sentence segmentation. Some of these aspects have their own components. Part of speech tagging consists of text, lemma, part of speech, tag, dependency, shape, is alpha, and is stop. The text is the original word text, and the lemma is the base form of the word. Part of speech describes simply the part of speech of the word. Tag provides a detailed description of the part of speech. Dependency describes the syntactic dependency of the word, also known as the relationship between tokens. Shape is the word shape. This consists of capitalization, punctuation, and whether or not the character consists of digits. Is alpha determines if the token is an alpha character, and is stop determines if the token is part of a stop list. Dependency parsing consists of text, root dependency, and root head text. The text is the original noun chunk text. The root text is the original text of the word that connects the noun chunk to the rest of the data that is parsed. The root dependency is a dependency relation that connects the root to the head. The root head text is the text of the root's token head. Dependency parsing uses head and child to describe words that are dependent on one another. Text is the original token text. Dependency describes the syntactic relationship between the child and the head. Head text is the original text that composes the token head. Head part of speech describes the part of speech tag that the token head possesses. Children are the immediate syntactic dependencies of the token. Named entity recognition consists of text, start, end, and label. Text is the original entity text. Start is the index of the start of the entity within the document. End is the index of the end of the entity in the document, and label is the label entity. Within named entities, there exists an IOB scheme where the token is to be considered I, inside the entity, O, outside the entity, or B, at the beginning of the entity. Tokenization consists of 4 aspects: prefix, suffix, infix, and an exception. The prefix are the characters at the beginning, suffix is the characters at the end, and infix is the characters in between tokens. The tokenizer exception is a rule where strings are split into several tokens to prevent the token from being split where punctuation rules apply. I also wanted to briefly review potential installation and usage of spaCy. So I went through the quick start guide within spaCy's site, which walks through the installation. So you would select your operating system. In my case, I would be using Mac OS. You can pick your package manager. I used pip, although I found when I was installing on my machine, it was unable to download, so I had to use pip 3. You can select your Python version if you're using 2 or 3. In my case, I was using 3. I decided to download the lemmatization package just to learn more about the tool. And you're also to select which language modules you want to use. In this example here, I picked English and multi-language. In my original installation, I had downloaded all of the languages, but then I found when I was just analyzing the text, I was only analyzing English text, so the other languages were not needed. At this stage in the install, you can also decide which languages you want to use. spaCy has models in English, German, French, Spanish, Portuguese, Italian, Dutch, Greek, Norwegian, Lithuanian, and the multi-language model. If any of these language options don't suffice for the use case, there is a tool called Prodigy that allows for users to create and evaluate own models that they could use for different languages. As you can see from the output, if the token is a word, it describes its part of speech as well as the dependency and shape, and if it is alpha or stop, if it's punctuation, it claims that it's punctuation, and then the remaining factors are rendered to be false as it is not text. I have implemented 2 examples utilizing the spaCy tool. In the first example, I used Google Colab to implement the library. The corpus I used was from Julius Caesar, and I used the English language as the text was originally in English. The tool identifies words and punctuation and separates them by text, lemma, part of speech, tag, dependency, and shape, and it determines based on true or false if the token is an alpha or if it's a stop. I also implemented one of the visualizers. I used the dependency visualizer. In this example, I used spaCy from spaCy, and I used Binder that was embedded within spaCy's website. So again, I used the English language, and the sample sentence I used was the quick brown fox jumps over the lazy dog. I also used the render function within spaCy to generate this image, and this image shows the dependency of each word in the sentence on other words within the sentence. As you can see, the dependency rendering also shows some of the part of speech of the words within the sentence. I would have implemented other visualizer examples within this text. However, the sentence was too simple to have the entities recognized, and it was unnecessary for the long text visualizer to be utilized. Seeing as spaCy has the ability to utilize different language models, I decided to test this capability out. In this example, I used the Italian model, and then the corpus utilized was from an Italian book called Il Porto Sepolto, and then I just ran the same example as in English. What I found interesting in this example was, as Italian has nouns that are considered to be masculine or feminine, spaCy actually is able to identify whether or not the noun is plural or singular, and if it is a masculine or feminine noun. So as we can see here with this example, again, it describes the text, the lemma, the part of speech. The part of speech then contains whether or not the noun or verb is masculine or feminine. If the verb modifies a feminine or masculine noun, that's where it establishes that within the output. There's the tag, the dependency, the shape, and whether or not it is alpha or a stop word. Stop words are different between languages, so it was interesting to see the ability that this tool has in reference to other languages. All of the data and information I used within this presentation was gathered from spaCy's website.